Today we're going to talk about inductors and their relationship to capacitors. Before you is standard electrical circuit. You'll recognize the symbols for a battery and resistor, but once again you'll see a new symbol, and this is a symbol for an inductor. Okay? Inductors in general are coils of wire. They are the complement to the capacitor. So they are the complement to the capacitor. Inductors are analogous to capacitors. All right. Capacitors mainly affect voltage, and they do that by storing energy in an electric field. All right. Inductors, they mainly affect current, and they do that by storing energy in a magnetic field. Okay. So once again, they are analogous to each other, but remember, capacitors affect voltage, and they do that by storing energy in an electric field. Inductors affect current, and they do that by storing energy in a magnetic field. All right, once again, inductors have a wide range of uses, everything from electric motors to filtering circuits to radio tuning. In fact, in an alternating current situation, if you combine an inductor and a capacitor in a similar circuit, whether in series or parallel, it'll actually resonate at a certain frequency. They have differences on real and imaginary power, and we'll get it all into the AC applications of inductors and capacitors later. An inductor, what it physically is generally simply a coil of wire. All right, an inductor is simply, in general, a coil of tightly wound wire. Okay. Now, we're going to introduce Maxwell's theorem here. So, anytime what Maxwell's theorem states, and Maxwell's theorem is the basis for radar and any kind of electromotive force, basically says Maxwell's theorem states that anytime you have an electric field, so anytime you have an alternating or a varying electric field, anytime you have an electric field that is a function of time that varies, you will also have a magnetic field. Also have or produce a magnetic field. And magnetic field is B. It'll produce a time-varying magnetic field anytime you have a time-varying electric field. And those two are going to be at right angles to one another. At right angles to one another. So in the case of this coiled wire, anytime we have a current flowing through this wire, so anytime you have a current flowing through this wire, you're going to actually have a magnetic field at 90 degrees to it. In this case, it's going to be going around the wire. You can take it by your right-hand rule, essentially. However, whenever we take this wire and coil it, these coils on this side will go around this way. On the bottom, they'll go around this way. On the outside, they'll go into the page. On the back side, they'll come out of the page. All these magnetic fields, whenever you coil the wire like this, will line up so that the overall magnetic field is pointing like that. Okay? So, how does that affect our actual circuitry? Well, what it does is it causes, let's say, current over time. So let's start at zero current, and let's close the switch on this circuit and start the current flow. Without a capacitor, it would pretty much jump instantaneously up to whatever the current flow was dictated by the resistor, by the resistance of the circuit. Okay. However, with an inductor, it's going to slowly and exponentially build up to that current flow asymptotically. Okay. The same thing will happen whenever we shut it off. Step function down without the inductor. However, with the inductor, based on the energy stored in the magnetic field, and remember, each time you change an electric field, it changes the magnetic field. Each time you change the magnetic field, it changes the electric field as well. So it's going to decay exponentially back down to 0. All right, so it's going to resist a change in current flow. Another a hydraulic analogy is simply a water wheel in a river. Okay, so here you have a river. Water's flowing this way. And let's say you have a water wheel here. Whenever you first put the wheel in the water, it's going to be turning very, very slowly. And eventually, it'll get to full speed. And then whenever you shut the water off, the wheel is going to continue to turn around in a circle until it slows down. That's essentially what happens with an inductor. And it's a way to store energy. All right. So, how much energy itself is stored? Okay. How much energy is stored? Well, similar to the capacitor, we can do the integral equation, or else I can just give it to you. I'm not going to derive it this time. But the energy stored in an inductor is equal to 1/2 the inductance times the current squared. Remember, for a capacitor is 1/2 the capacitance times the voltage squared. So once again, there's your analogy there, where inductors affect current, are affected by current, and capacitors are affected by voltage. Okay. What about the actual voltage through your inductor? Well, your voltage through your inductor over your inductor is going to be equal to your inductance times the derivative of your current with respect to time. Okay? Just as so, the AC equations we'll get into later. This is about all for the inductors as far as the current and voltage equation goes through. One thing to note, that once it reaches steady state, the voltage through the inductor acts as a short circuit in a DC circuit once it reaches a steady state equation. Okay. Now, how do inductors act in series and in parallel? Well, they act just like resistors. All right, so in series, L total equals L1 plus L2 plus L3. And in parallel, 1 over L total equals 1 over L1 plus 1 over L2 plus 1 over L3, all the way to 1 over Ln. And once again, that's all the way to Ln out there. All right, so remember, capacitors are the opposites of resistors. So for capacitors, it's the opposite of resistors. Series is the 1 over relationship. So the series relationship is 1 over C total equals 1 over C1 plus 1 over C2 all the way to 1 over the Cn. And then in parallel, capacitors act like resistors do in series, or inductors do in series. It's simply C total equals C1 plus C2 plus C3 all the way to your final C. Okay, so that's just a comparison of inductors and capacitors and your basic construction of it and how they work. We'll start getting to the terms of reactance and imaginary and real power and impedance and all that other kind of, and angular frequency, and how AC circuits affect those in the next few videos.